Hi everyone, welcome to another remote session of statistical models. This is the video for week 7, part 1. And today we're going to talk about, for the first time, a concept that's not directly related to multiple linear regression. We're going to talk about this model that we can use to analyze data called one-way Anova, where Anova, again, stands for analysis of variance. So specifically for the week 7 slides, we're going to talk about the model itself, this one-way Anova model, which we use to compare mean response values across different groups. We're going to talk about how to assess the model assumptions, see if they're met, and how to use the model and interpret the results. And then lastly, although we won't get to it in this video, is we're going to talk about use of Fisher's least significant difference, LSD. So to start, for one-way Anova, so this is very similar to multiple linear regression in a number of ways. So we've already seen how using multiple linear regression, MLR, we can model a single quantitative response using several predictors or explanatory variables. So Anova, one-way Anova specifically, is for this very specific case where we, again, have a single quantitative response, just like regression, but we only have one single categorical predictor. And so this is called a one-way analysis of variance. And actually, this is a very specific case of multiple linear regression. So they're entirely equivalent in their results, in that you'll get the same conclusions using a linear regression model where you have just the same quantitative response and then a categorical predictor, a single categorical predictor. So you might ask fairly, why do we even bother learning Anova then if it's already covered by multiple linear regression? Multiple linear regression is just a generalization of it. Well, Anova was commonly used for a very long time in place of multiple linear regression in these cases. And a lot of people still use it to this day in, say, research articles and other studies. So the problem itself is formulated differently, even though it gives equivalent results. The numbers and terms and stuff that we deal with are different. So we'll have to talk about it in order to understand the process of implementing an Anova for our analysis. So it'll be useful for understanding other people's analyses that they've done for data sets, even though it gives equivalent results. Although personally myself, if I'm ever going to analyze a data set, I would just always use regression because it gives you the same results and it's, I think, more straightforward. But anyway, we'll cover it so that we can understand when other people use Anova. So some examples of questions we can answer using a one-way Anova. First one, does the average or typical GPA differ between different majors for students at Augsburg, depending on what they're studying? So that our single quantitative response would be GPA. Our categorical predictor is student major, which has several levels. Another question, does the average or mean textbook price vary by the department? So maybe math books cost more than, say, Spanish books. So in this case, the cost of the textbook is our quantitative response. The department is our categorical variable, categorical predictor. And lastly, sort of like a public health question we could answer, does that mean blood pressure differ for different types of medications? So say we have 4. So our categorical predictor would be the medication that we're considering, and then the response is the blood pressure. Okay, so these are all questions we could answer with a one-way Anova. And you might recall we've already seen this analysis of variance come up in this course, specifically when we looked at an Anova table for our regression analyses. But these were not exactly the same as this one-way Anova. So statisticians like to reuse names, unfortunately, for different concepts. So that was also called Anova, mostly because it was dealing with variability, so an analysis of variance. But it's not the same as this one-way Anova model. So just revisiting that Anova table for multiple linear regression, as a reminder, we have the response variable being y, that's our quantitative response, and we have the sample mean, which we're going to denote with y bar. And we have this key important Anova sum of squares identity, which is SS total equals SS model, the variability explained by our model, and then plus SSE, the variability unexplained by our model, where SS total is the total variability in the response. So this key equation there was important in formulating this whole Anova table, which allows us to test the statistical significance of our overall regression model. So we have all these terms again, where K is like our number of predictors, N is our number of observations in our data set. This is our degrees of freedom column, DF, our sum of squares column, SS, and our mean squares column. And then lastly, this is our F-test statistic, which we use for testing our overall significance of our model. Okay, so again, this is the Anova table for multiple linear regression, but this is different than one-way Anova, using a one-way Anova for analysis. So we're going to talk about the one-way Anova for analysis today. And again, I defined these terms in the multiple linear regression model for the Anova table. Oh, and as a quick reminder, as a quick reminder, sorry about that. As a quick reminder, we can calculate a lot of values from each other using this table. So for example, if we know the SS model and the SSE, we can add those together to get the SS total. Additionally, for example, the SSE divided by the degrees of freedom error, this term gives us the MSE. So SSE over n minus k minus 1 gives us MSE. So there's a lot of nice relationships in this table like that that are useful to know how to calculate. Okay, and as a quick reminder, we use this Anova table specifically to test our overall model, which is equivalent to testing if all of the slopes for each predictor variable are simultaneously 0. So if they're all 0 at the same time, versus at least one predictor is important or linearly related to the response. So this overall F-test allows us to test this null hypothesis, and we obtain a p-value for testing this specifically using R. Okay, but the one-way Anova model that we're going to use for analysis is a different way to view this partitioning of the variability. So it's a statistical test, actually, not just a table. So, and it's useful if we want to compare the average response across different levels of a categorical variable or different groups. So if we recall, I can't remember if this is a required course for this class, required prereq, but in introductory statistics classes, nearly all of them cover what is called a two-sample t-test. And so this hypothesis test is useful for comparing the average response value between just two groups, specifically when you only have two levels of your categorical variable. So for example, we could use a two-sample t-test to test if the average ACT scores of Augsburg students differ from students at the University of St. Thomas. And so our formal hypotheses for these And I think this is supposed to say GPA actually instead of ACT, but that's okay. The formal hypotheses for these is that the average ACT score is equal for Augsburg students and St. Thomas students, and the average ACT score differs for Augsburg and St. Thomas students. Again, this is supposed to say GPA in my example, so I'll update that accordingly. But yeah, looking at this example, I wanted to show an example of analyzing this type of thing. So sort of an aside using R here, I'm going to have a little fun and show you guys how you can do that as well. So I just wanted to compare Augsburg and St. Thomas students. And I don't actually have data on these GPAs for Augsburg and St. Thomas students, but we can simulate it or make up fake data using R and then plot it accordingly. So here, I'm loading these packages actually because I want to, and again, this is not directly relevant to the course. I just thought it would be fun to show you guys what R can do sometimes, some cool things. So these packages are going to be useful for grabbing an image online. Specifically, I was grabbing a logo for St. Thomas and Augsburg University, and then using this function that someone posted online to extract the colors from the images so that we can then plot using those same colors in R, which is kind of cool. So yeah, so these are posted in the slides so you can see if you want. So here I'm grabbing the, it's cut off, but this just closes with 2 parentheses because the URL is pretty long. This is reading an image from online from Augsburg's website. This is reading an image online from, that's a logo for St. Thomas, University of St. Thomas. And then I'm extracting the colors from these images actually. Okay. And then using those extracted colors, I'm, well, not yet. First, I'm simulating GPA values for students because I don't actually have real data on student GPAs at Augsburg and St. Thomas. So again, you don't need to know how to do this. I was just showing this in case any of you are interested for fun. So I'm simulating GPA values, and then I'm actually just forcing them because randomness, they could jump outside 4.0. It could be above 4.0 or below 0 by random chance for their GPA. So then I fix that manually. I just set it to 4 if it generated a GPA that was like 4.1 for some reason. And then we can plot it to get a feel for what this data looks like that I just simulated. And here's where I'm using the colors that I grabbed from the websites for Augsburg and St. Thomas to actually use the school's main colors. So I thought this was kind of cool, so I wanted to show you guys that R can do this. Sort of grab those colors, grab those images, extract the colors, and then plot them accordingly. So this is like Augsburg's main colors, right? And University of St. Thomas's main colors, purplish type thing. Anyway, so here I'm plotting these GPA values for 50 students from each school. But again, I just simulated. It's actually kind of fake. But yeah, we can see like Augsburg had like 1 student with a 4.0. St. Thomas had 2 students with a 4.0. But it does look like on average, Augsburg students are have a higher GPA than St. Thomas. So good on you guys. You're one-upping them. So yeah, so what we can do with a t-test is if we have these GPAs for each student, which is a quantitative response, we can say, do Augsburg students on average have a higher GPA than St. Thomas students? So that's a question we can answer with a 2-sample t-test. Based on the plot, it looks like it. They're higher a little bit on average, but we can formally test this with a hypothesis test. So we're going to use this t.test function in R. So this is good to understand this slide here, how to do a t-test. And I'm testing Augsburg students' GPAs versus St. Thomas students' GPAs, and then I'm doing a two-sided test, so just seeing if they're equal or not. You can do a one-sided test to test if you wanted to answer the question, do Augsburg students have a higher GPA on average? Then it would be a one-sided test. But here I just want to see if they're different or not. This var.equal is just an option for if we want to assume that the GPAs for Augsburg and St. Thomas students have equal variances. So is the distribution, the variability in the points the same between the two groups? So yeah, the spread seems pretty similar, not that different. So I think equal variances could be true here, but the more conservative option is always just to assume that you have different variances. It's just more generalizable and you're making less restrictive assumptions. So in general, I say just use variance, equal variances equals false here. And then we want to test at the 5% significance level, or in other words, a 95% confidence level. So I specify that here. So the results of this t-test are displayed here. What we're most interested in are the confidence interval and the p-value. So here, how we interpret this is, type this on the slide here. Oops. Type this on the slide here, is that since the p-value of this number is less than 0.05, we have evidence at the 5% significance level that Augsburg students at the GPA of Augsburg students differs from that of St. Thomas students on average. All right, and actually what we can see is that because the confidence interval is entirely positive and we had Augsburg students first, we can actually say that Augsburg students have a higher GPA on average. So we can also look at the sample means here to determine that. This is the average GPA for Augsburg students, average GPA for St. Thomas students. So they're different, but which one's higher? So that's important to mention. So we have evidence at the 5% significance level that the average GPA of Augsburg students is higher than that of St. Thomas students. Okay, and I already said on average. So to recap, since the p-value of this is less than 0.05, we have evidence at the 5% significance level that the average GPA of Augsburg students is higher than that of St. Thomas students. That's how we interpret these results. Okay, for the hypothesis test. For the confidence interval, we can interpret that here too. So we say here we are 95% confident that that Augsburg students have between GPAs between 0.09 and 0.30 units. I don't think there's actually units, grade units or something for GPAs. Higher on average than St. Thomas students. All right, so we are 95% confident that Augsburg students have GPAs between 0.09 and 0.30 units higher on average than St. Thomas students. And I got those values from here. Okay. So that's how we'd interpret the confidence interval. Okay. So that's a two-sample t-test, which are good, important to understand how to do a two-sample t-test. But what if there's more than two groups? So here we only had just two levels, Augsburg or St. Thomas. In general, we might compare three schools, in which case we can't use a t-test anymore. Those are only useful when we have two groups. So this is where the one-way Anova model comes in handy. So this is formulated as, for the one-way Anova model, we're assuming our response for each observation is equal to a group mean. So for example, we had like mean Augsburg student GPA, and then plus some random noise, some error term here. Because not every student within Augsburg has the same exact GPA. We assume they sort of are random fluctuations around this average GPA within Augsburg. So in other words, it's the response. Each response is equal to the overall group mean for that specific group plus some error or noise. Okay. So this is called like the group means formulation of the Anova model. All right. And if we recall back to the Palmer penguins data, so we sort of had three different groups in the species. We had these Adelie penguins, the chinstrap penguins, and the gentoo penguins. And we can compare their average bill lengths across the groups. So for example, here we have all the bill lengths for the Adelie penguins, and I put points overlaid on these box plots here, chinstrap penguins and the gentoo penguins. So the points just are the raw values, the bill lengths for each individual penguin within that group. And then the box plots, what the box plots tell us is the bottom line of the box plot here tells us the first quartile of that group. So the 25th percentile for Adelie penguins in terms of bill length is this line here. So about like, I don't know, 48 or no, 38 maybe. This middle black line, which is a little bit covered up by the blue line here, is the median value, the 50th percentile within this group. That's what the box plot tells us. And then this upper line for the box in the box plot is the 75th percentile, or the third quartile. Okay, so the box plots convey a lot of information. And also, just since the Anova model is comparing group means, I added lines to this plot, these horizontal lines for each group that represent the mean response value within each group. So often that will be similar to the median. For symmetric data, they're perfectly equal, the mean and median. Here, there can be a little bit different, but so this blue line is telling us the average bill length for Adelie penguins is about 39. For chinstrap penguins, the average bill length is about 49. And for gentoo penguins, the average bill length is about 48. Okay, so a lot of information conveyed in this plot. But yeah, so this sort of motivates, this is a way to visualize this difference in the group means here. We can see they're quite a bit different. There's quite a gap in terms of the average response values within each group, average bill lengths. So this, we can use a one-way Anova to formally test if the penguins differ on average in terms of bill length by species. Okay, and so to formally state these hypotheses with this group means approach, we state them as HO, that all the mu's are equal, where mu sub 1 is the average response for the first group, and so on till the kth group, And then the alternative hypothesis is just that at least one pair of the groups differs in their average response. So for example, up here, it looks like the chinstrap and gentoo penguins might be similar. They're pretty similar on average in terms of their average bill length. But since the Adelie penguins are different, so at least one of them is different from the others, this would favor evidence for the alternative hypothesis for a one-way ANOVA. Okay. And so to test this, we get another F-test statistic, very similar to before. And this will actually be the same F-test statistic as from the value will end up being the same as from the multiple linear regression approach for testing the overall model. That's where the equivalence comes in again between the multiple linear regression approach and the one-way ANOVA. And we can get a corresponding p-value and test and compare it to 0.05. So this isn't the only formulation of the problem, though. So instead of doing a group means approach, we can think about it as a group effects approach. So this is, again, equivalent, but a slightly different formulation. So in this way, people think of it as that there's this grand mean response for all the data pooled together. There's an average bill length for all penguins. And then within each group, there's this effect, okay, alpha sub k. And then there's random noise added to each point as well. So this is slightly different than the group means formulation. So actually, before when we had group means being the mu sub k's, that's equal to the overall mu plus this alpha sub k. It's just expanded out into two terms here instead. Okay, and I know this is sort of getting into, again, why do we have to do the same thing using a different way? Well, yeah, I'm not a fan of that either, but people, take these different approaches when they're analyzing data in real life, like in research articles and, jobs at work. So it's good to understand both formulations and how they're equivalent and what they mean, because it'll help us understand other people who do these analyses. So even if you don't like doing stuff in a bunch of different ways, that's fine, but and understandable. But it's good to understand these different ways, because then we can understand other people's analyses that they've done for data sets. So yeah, so we have this essentially in words, we're assuming each response is equal to an overall grand mean, which is the same for each observation, plus a group effect, which is the same for observations within each group, and then an error term, which is specific for each observation. Okay, and so if we visualize this, back to the box plots, this black dotted line is representing the grand mean, that mu value. That's the average response, or here the average bill length for all the penguins pooled together. Whereas the blue line is still the mu sub k, the group-specific mean. If we want to visualize the alpha sub k's, so the alpha sub k for the Adelie penguins, that group-specific effect, is going to be this distance between the overall grand mean and the group-specific mean. So here, the alpha sub k for the Adelie penguins is going to be negative, because alpha sub k is like sort of the shift from the overall grand mean. So actually, since the Adelie penguins have a lower bill length on average than the grand mean, the alpha sub k for the Adelie penguins is going to be negative. And then similarly, for the chinstrap penguins, this distance here from the dotted black line to the green line is going to be positive. So the alpha sub k for the chinstrap species is going to be positive because this distance from the green to black line here is positive. So this is just a way to visualize the different formulations of the Anova model here. Okay, and sort of similar to before for the group means approach, we can test these hypotheses again, that essentially now it's testing that not just that the group means are equal, but that the group effects are all 0. Because the idea is that if all the group effects are 0, that's the same as all the group means being just the grand mean being the same. And the alternative hypothesis here, which again is equivalent to the other testing procedure for the group means formulation, is just that at least one of the group effects is different than 0. In other words, this means at least one group differs in its average response. Okay. So we'll continue talking about the one-way ANOVA next time in the part 2 video for week 7. But that's it for today. So thanks, everyone.